Good morning, everyone. I am Mr. H. Thank you for joining me. We're doing here an introduction on infinite geometric series and/or sequences, a topic that you learn at the end of your first year calculus class, the Calculus 1 single variable, and it's usually at the end because it's a harder topic in terms of concepts to understand. An infinite geometric series, let's look at that in a generalized sense in this particular video. When you're looking at this geometric series 2, 4, 8, 16, you know how this ends up going. When you're looking here at this infinite geometric sequence, you know the last number will be infinity because it's going to go up to infinity in terms of the n value. And each of these can be written here in terms of a rule. This would be 2 to the power of n. And you're looking at this from 2 to the power of 1 all the way up to 2 to the power of infinity. And that's exactly what you have. Contrast this sequence over here with what I'm going to put for you right here. 1 over 2, 1 over 4, 1 over 8, 1 over 16, and then you'll have here 1 over infinity, which will really be equal to a 0. The rule you could establish for this specific sequence, infinite geometric sequence, because the n values are always going up to infinity, is this. You'll have 1 over 2 to the power of n, where you're looking at it from 1 all the way up to infinity. That's exactly what you have here. You're looking at it from 1 to infinity, here 1 to the infinity. But look at these. In each instance, that is the rule that is being established for this infinite geometric sequence. In each of these cases, you can easily establish something called an R value, which is your common ratio, which represents the ratio between your succeeding number and the number right before. Take any of these two numbers, 8 divided by 4, or you can do 16 divided by 8. In each instance, you're getting an R value 2. Look at this second sequence and you can establish another R value. You can do again 1 over 8 divided by 1 over 4, or you can do 1 over 16 divided by 1 over 8. You can flip these fractions out. You'll always have here a value common ratio of 1 over 2. Contrast these. In this instance right here, when you're looking at this R, your common ratio, look at it. It's a value larger than or equal to 1. It's 2. It's larger than 1. In this instance, your R value is less than 1. And a very particularly interesting phenomenon comes about as a result of these differences. Whenever your R value is less than 1, the common ratio is less than 1, and you were to sum up all of these numbers, this sequence, if you were to look at it in terms of a series and you were to establish the sum of that series, infinite geometric series, here you'll end up with a good finite value and you would see convergence. In this particular instance, when the R value is greater than 1, here it was 2, you were to do a sum of all of these numbers in the series, you'd get an infinite value. It would not be finite, it would be divergence. Here you see convergence, here you would see divergence. Something similar to area below the curves for those improper integrals. So this is a fact you must remember. When the common ratio is greater than or equal to 1, you will see in terms of the series a sum from n going up to infinity, always a value which is divergent infinity. And here for the convergence cases, you'll have a good finite small value. It doesn't have to be small, but it would be a finite, clearly established value, and it would definitely not be infinity. This right here lays out the premise for what we're seeing now in the rest of the video. Now, just for a little bit of confidence building, let's look at this first infinite geometric sequence. You know you're looking here from n is equal to 1 all the way up to n is equal to infinity. But what if you were to find a particular value? You know a1 is always your first term, which is 2. But what if I told you to find me a specific value within that sequence, like an, and I'm telling you to find me the sixth value? For this, it's easy. You can easily extrapolate it. But there's a specific formula you should ideally know for doing that. Your nth number in your infinite geometric sequence, or any type of geometric sequence would be always your first number times r to the power of n minus 1. And you could just plug away here. You know your first term is a 2. Your common ratio here is a 2 because each number is twice the previous. To the power of 6 minus 1, you'd have 2 times 2 to the power of 5, which would be 2 to the 6, and that would be 64. First, second, third, fourth, fifth would be 32, and the sixth number would be 64. Now, what if I told you for this sequence, find me the sum of these first 6 numbers? Well, there's a formula for that, and you should know that too. The sum of a given number of items in that infinite geometric sequence or geometric sequence is the sum of the numbers in that sequence, which now we're referring to as a series because we're looking at the sum, would be a formula you would have to know. The first term times 1 minus r to the power of n over 1 minus r. That would be the formula, and you would have to do just plugging easy values here. The value for the first one you know is what? It's 2. Then you have 1 minus common ratio, which is 2 to the power of 6 over 1 minus 2. R here is your common ratio. You would just have to do this. You'd have 1 minus 64 times 2 divided by minus 1. You'd have a value here equal to a positive 126, and you can easily add these numbers and you can verify that your answer would be good. Just add these 6 numbers: 2 plus 4 plus 8 plus 16 plus 32 plus 64. We have 126, and we're good in both of these instances. So this is some little bit of stuff you should be aware of, because this little bit of stuff will play into the remainder of the material that I'm presenting you in this video, which is the relevant part, perhaps the most relevant part. And we'll quickly dispense with this. This is a format in which you look at these type of questions. You have your specific function over here, you want to call that. You're looking at n value from 1 up to infinity. This will represent an infinite geometric sequence. And when you're looking at their sum, then that is viewed as an infinite geometric series, because you would first establish your sequence 2 to the 1, 2 square, 2 cube, 2 to the 4, all the way up to 2 to the power of infinity. There's no point for you to do this in terms of their sums: 2 1 plus 2 square plus 2 cube plus 2 4, all the way up to 2 to the infinity. Why? Because you know here your common ratio is equal to 2. Any number here, exceedingly large number, will always approach infinity, and that will be the sum of your infinite geometric series. So this question is right here pretty much dead, because we're done with it. Your common ratio here, as I told you, is greater than or equal to 1. In these instances you'll see divergence, and there's not much more you can do here. The most interesting parts come around when you're looking at the convergence cases, which is what we will look at next. But this right here represents your terminology. The sum of all the numbers in your sequence, represented here in the series format from 1 up to infinity, for this will be infinity. The case is quite different when you're looking at this, because here you know you're looking at a sequence which looks like this: 1 over 2 to the 1, 1 over 2 square, 1 over 2 cube, 1 over 2 4, all the way up to 1 over 2 infinity, which you know is zeros out, because as these exponents get larger, the denominator in conjunction with its numerator, this rational function, is becoming smaller and it's approaching 0. But to determine this right here would be interesting here. Here you're looking at an infinite geometric series now, because the sequence will be looked at everything in terms of its sums. But there's a specific formula you have to learn here, and that formula is not hard because it adapts very well from what I've shown you already. This formula right here, Sn, the formula for Sn. And this is very similar to the limit of sums as those sums approach infinity. You don't want to look at these type of questions here, 1 over 2 to the n from 1 up to infinity. You don't want to look at them in terms of integrals like areas under curves, because you cannot look at it that way. You have to look at it in terms of limits. When you're looking at this limit as n approaches infinity, you know the formula was this. You're looking at your a first term, 1 minus r to the power of n over 1 minus r, as n approaches infinity. This is exactly what you're doing. Now when you open this up for these cases here, this is formula established clearly for these cases where the absolute value is less than 1, for your convergence cases where you know the sum of this infinite geometric series will be a finite understandable value. You have to look at it this way. Open this up and we'll establish the formula. You're looking at it, limit as n approaches infinity, you'll have a, I'm removing the 1 designation because we know we're looking at that, minus a times r to the n over 1 minus r. Now separate everything here across that numerator negative sign, such as this. You're looking at it like this, and you're looking at it like this. Limit as n approaches infinity, you'll have a over 1 minus r, minus that minus, you have a r to the n over 1 minus r. That's what we've established so far. You can play around here with these limits, and you can also play around with algebra here, because you see a common term which can be isolated, which is a over 1 minus r. A over 1 minus r, I'm isolating that. It goes into the first term 1. It goes into the second term, and with the limit coming into play, limit as n approaches infinity, it goes r to the power of n times. Now look at how everything very smoothly established itself. You can do a bunch of calculator strokes. This is exactly why I talked about this at the very beginning. If the r value is greater than 1 or equal to 1, like a value which is larger than 1, think about what would happen if that 1 value here is large. and let's do like 1.5 or 1.45, and let's start adding extremely large numbers to the power of, because everything here is to the power of n, you'll have 1.45 exponent 99. As you make these values, n values, larger for a common ratio which is larger than 1, this will become infinity and it will corrupt everything, and your entire sums of the geometric series will become equal to infinity. This case over here is most interesting when you're looking at the common ratios and they're less than 1. Let's come up with a value like 0.5 and do exponent 9. We're getting a decimal value 0.00195. Let's do 0.5 exponent 99, and we'll see it's getting to the power of minus 30. We'll do 0.5 exponent 999, and now it's zeroed out. Why did it zero out? Because this area over here became extremely small. And what you end up seeing as n approaches infinity, all of this right here, this entire aspect is just equal to a 1, which multiplies with this, and your entire formula becomes a over 1 minus r. This a over 1 minus r represents this, the formula for this. This limit of an infinite geometric series as n approaches infinity, for those cases where you are expecting convergence, the common ratio less than 1, is equal to this formula right here, and that's the formula you would apply right here for this case, and you'd see it would work out very well. We've established the formula to be this a over 1 minus r, 1 minus your common ratio. And now let's do this question right here. 1 over 2 to the 1 represents my very first value, because this is my n equals 1, and I'm looking at everything here from 1 up to infinity. My first term, we can be specific over here, 1 over 2 over 1 minus common ratio 1 over 2. When you do 1 over 2 divided by 1 over 2, we get a value here of 1, which is a finite value. This infinite geometric series will have a value here of 1, and it would be right. You wouldn't think it to be 1, but it would be right. Think about it. You're doing a half plus a quarter plus an 8 plus a 16th plus a 32nd, 64th. All of these are minuscule increases, initial large increases, but everything will equal out to a 1 in terms of their infinite geometric series sum. Let's look at now one defining question for this particular video, and we'll be good with that. Again, do not view these as your regular integral questions, areas below the curves. You don't view them that way. Our question is this: 3 divided by 2 to the n, going from n equals 0 to infinity. What would the infinite geometric sequence look like? It would be 3 over 2 to the power of 0 would be your first term, 3 over 2 to the power of 1 second term, 3 over 2 square, and then 3 over 2 cube, and then you're going all the way 3 over 2 to the power of infinity. This first term right here is equal to a 3, this here is equal to 3 over 2, this is 3 over 4, 3 over 8, and then this will zero out. So these are all your things. This right here is your sequence, but if you're looking everything here to determine this, then you look at everything as a series, the sum of all of these terms. What's the common ratio? And just pick any of these two numbers. You have 3 over 4 divided by 3 over 2. You'll have 3 over 4 times 2 over 3, which is 1 over 2. Here your r value is 1 over 2. Take any term and the number before and always divide them. You'll have a r ratio here, your common ratio of half. It falls right here in this scheme, so you know this infinite geometric series will have a sum which will be a finite value. Run it through the formula. You know, limit as n approaches infinity, this sum in terms of infinity is always your first term divided by 1 minus r. For convergent cases, your first term is a 3, you have 1 minus 1 over 2. a1 divided by 1 minus r, you'll have 3 over half, which is equal to 6, and that answer will be right. The sum of this infinite geometric series in terms of all of these values from 1, n equals 1 up to n equals infinity will be 6, and it will be right. And that right there will lay down the groundwork for the introduction you need for this specific topic that will come in terms of more videos later on. Remember to use this formula right here only for convergence cases. For divergent cases where you know r is greater than or equal to 1, you don't use this formula, because you know in this case your sum in terms of the n values up to infinity is always equal to infinity, because those values just become too large, out of bounds. Thank you for watching. Have a good day.